Now that we've learned how to make mass-mass calculations, we need to understand something about those calculations. When we make those calculations, we are assuming that reaction conditions are perfect, and that as a result, the reactions that we examine will go exactly as predicted by our stoichiometric calculations. So the first thing you need to understand is mass-mass calculations are said to provide us with theoretical yields. The truth of the matter is that any chemical reaction can be influenced by a number of external factors. Some of those factors are temperature, which is probably the most significant factor for any reaction. The container in which the reaction takes place, believe it or not, the makeup of a container can affect a chemical reaction. If there's a gaseous reactant or product involved, the pressure of that gaseous reactant or product can influence the reaction progress. The physical state of reactants, in other words, it makes a difference whether something is a solid, liquid, or gas, or in aqueous solution. And the last external factor is the experience and technique of the experimenter. Not everybody operates equally well in the lab.
No way.
The fact of the matter is, in most chemical reactions, some combination of the factors we just listed will prevent the production of the predicted mass of a product. In other words, what I'm saying here is the mass of product produced is typically less than the theoretical yield. In other words, the yield that would be predicted by our stoichiometric calculation. So in order to determine how efficient our particular reaction is, we calculate something known as the percent yield. Percent yield, as you can see here, is equal to the actual yield divided by theoretical yield, and because we're looking for a percent, we then multiply that by 100. One final comment here. Just as with percent composition calculations, I made a big deal about the fact that you can't have more than 100% of a chemical compound, nor can you have greater than a 100% yield in a particular chemical reaction. That would certainly be a violation of the law of conservation of mass. You'd be creating mass or matter out of thin air. One exception to this, if your product is contaminated, it is possible to get a greater than 100% yield. If that's what happens, you should automatically suspect contamination and not that you're some super chemist. Hopefully by now you've developed a routine and you've already got something to write on, something to write with, periodic table, calculator, and your handout of common oxidation numbers handy. Our first percent yield sample problem reads as follows. What is the percent yield in the following reaction if 5.50 grams of hydrogen react with nitrogen to form 20.4 grams of ammonia? What we're doing first, remember, is solving a mass-mass problem. I've got 5.50 grams of hydrogen. I want to know how much ammonia I can make from that. Well, before we go any further, let's make sure we're dealing with a balanced chemical equation. And what we're going to need here, it looks like a 2 right there, and that's going to necessitate a 3 there. So we've got a balanced equation at this point. Next, at some point, I'm going to need the molecular mass of ammonia. So I'm going to go ahead and calculate it right now, get it out of the way. Nitrogen is element number 7 on the periodic table. It's got a mass of 14 AMUs. It appears in the compound one time, so it contributes 14 AMUs to the overall mass of the molecule. Hydrogen is 1 AMU, and it appears 3 times. So we've got a total hydrogen contribution of 3 AMUs. That's a total of 17 AMUs. And remember, that's the mass of 1 molecule of ammonia. We're interested in a mole, so we know that a mole of ammonia is going to have a mass of 17 grams. Well, if I start with 5.50 grams of hydrogen, I need to convert that to moles. Well, it's really easy. 1 mole of hydrogen is 2 grams. Hydrogen is diatomic, and so that's how I get the 2 grams. Next up is the mole ratio step. What's the mole ratio between hydrogen and ammonia? Well, for every 2 moles of ammonia, how many moles of hydrogen do I have? And if you look at the balanced equation, you'll see I've got 3 moles of hydrogen. Remember, this is the only step in the solution process where the coefficients in the balanced chemical equation get used. Well, at this juncture, what I need to do is convert moles of ammonia to grams of ammonia. 1 mole of ammonia, and it's going to go down here in the denominator so that moles cancel out, that is 17 grams. And we know where that came from right here. Well, slide down here, give myself a little room, and once I do my math, I find out 31.2 grams of ammonia. Now remember, this is the theoretical mass of ammonia that should be produced. In other words, if all conditions were ideal, I would get 31.2 grams of ammonia. Well, the problem as stated says you only got 20.4 grams. So to calculate our percent yield, what we're going to do now is take the actual ammonia that we produced, which is 20.4 grams. We're going to divide it by the theoretical, which is the 31.2 grams that I just calculated. We're going to multiply that by 100 to get a percent, and that's going to give me 65.4%. And so my percent yield for this first sample problem is 65.4%. Here's another percent yield sample problem. Dichlorine monoxide, obviously a molecular compound with a name like that, it's sometimes used as a powerful chlorinating agent in research. It can be produced by passing chlorine gas over heated mercury 2 oxide according to the reaction below. If you begin with 2.14 grams of mercury 2 oxide and produce 0.71 grams of dichlorine monoxide, what is the percent yield? Remember, these problems are fundamentally mass-mass problems, and every mass-mass problem begins by simply balancing the equation. So I place a 2 there in front of that diatomic chlorine, and I've now got a balanced equation. Since I'm working a mass-mass problem, I need to take care of some formula and molecular mass calculations. I'm going to begin this problem with mercury 2 oxide, so let's calculate the formula mass of mercury 2 oxide. Mercury is element number 80 on the periodic table. If you look carefully, you'll see that it lists as its mass 200.59 AMUs. Well, mercury is another one of those that we're not going to round off to the nearest whole number. We're going to use 200.6 AMUs for mercury. Oxygen is still 16 AMUs. And what that means is the mass of mercury 2 oxide is 216.6 AMUs. Remember, we're going to be interested in a mole of mercury 2 oxide here momentarily. The other molecular mass that we're going to need is that of dichlorine oxide. Chlorine obviously is 35.5 AMUs, and there are 2 of them. So that gives us 71 AMUs from chlorine. Oxygen, 16 AMUs again. There's 1 of them. And so we end up with a molecular mass for dichlorine monoxide of 87 AMUs. I'm ready to go now and solve my mass-mass problem. The first thing I'm going to do is start with 2.14 grams of mercury 2 oxide, and I'm going to convert it to moles. 1 mole of mercury 2 oxide, well, it has a mass of 216.6 grams. Next up, our mole ratio step, the only step where we can use coefficients from our balanced equation. What's the ratio between dichlorine monoxide and mercury 2 oxide? Well, it's 1 to 1. There's 1 mole of dichlorine monoxide for every 1 mole of mercury 2 oxide. And now that we've got moles of dichlorine monoxide, we can convert that to grams using this molecular mass up here. In 1 mole of dichlorine monoxide, there are, as we've already calculated, 87 grams. And so we do a little calculator work, and we find out that this is 0.860 grams of dichlorine monoxide. That's our theoretical yield. Ideal conditions, that's what we would get. Well, what's our percent yield? The problem tells us that we only produced 0.71 grams of dichlorine monoxide. Our theoretical is 0.860 grams. Again, we're going to multiply that by 100 so that we get a percent, and it yields 82.6%. And I wouldn't round off to a whole number. I would simply go to 1 decimal place with these percent calculations, and that's actually quite a good yield for a chemical reaction. Okay, here are your 2% yield practice problems. Number 1 says you burn 10.0 grams of methane in an excess of oxygen and form 19.8 grams of water. What is the theoretical yield and the percent yield? I've given you the answer to both of those questions in red. Make sure you start by balancing the equation there. And furthermore, remember 10.0 grams, that is 3 significant figures. You're not entitled to drop that last 0. Number 2, if you start with 1.30 grams of copper, use excess nitric acid and obtain 1.40 grams of copper 2 nitrate. What is the theoretical yield and percent yield? Again, I've given you the answer to both of those questions here in red. Make sure you balance this equation, and as a hint here, what I would recommend is get 4 nitrogen on each side, and I think you'll find balancing to be quite easy. Good luck.
War's over, man. Wormer dropped the big one.
What? Over? Did you say over? Nothing is over until we decide it is. Was it over when the Germans bombed Pearl Harbor?